So I want to talk about the molecular orbital description for the Diels-Alder reaction. I know we didn't have time for this in class, so I think it might be useful for us to go over this just in the video. Klein talks about this in the book. I'm hoping that with his description and my description, it will make some sense so that when you do your homework, you'll be able to do it without too much difficulty. So what we're going to talk about is the orbital analysis of the Diels-Alder reaction. And then I hope you can apply this when you're thinking about 2 + 2 or 4 + 4 reactions. So the key for us is to understand the molecular orbital description for the dyene and the dienophile. Right? So we need the MO description of the dyene and the dienophile. Right? And what we're going to do is take the simplest case, which is butadiene plus ethylene. Okay, so the simplest dyene and the simplest dienophile. Let's look at the molecular orbital description, and then we'll see how we can explain why the reaction works. So if we look at ethylene, and we think about what the MO description for ethylene looks like, when we build up molecular orbitals, we bring atomic orbitals together. Right? The theory is often called the linear combination of atomic orbitals. So we're thinking about taking a p orbital plus a p orbital, and then bringing those together. We bring 2 orbitals together, we're going to get 2 orbitals out, right? And the thing to remember is that we can combine these to get a bonding molecular orbital and an anti-bonding molecular orbital, right? And hopefully, as you remember from previous chemistry classes, bonding molecular orbital, we're going to have the same phase of the p orbital, so that we get a bonding molecular orbital, and up here we're going to have a node because we don't get constructive overlap. Right? I'm going to use shaded and unshaded. Klein uses color red and blue. Right? So here we have bonding. So this is going to be psi1, which is bonding. This is going to be psi2 star, which is anti-bonding. And then the question is, where are the electrons? Well, when we have a pi bond, pi molecular orbital, we're going to have 2 electrons, and they're going to be in the bonding. That's why we have a bond, right? And if we look at this, we need to be able to analyze it for where the highest atomic molecular orbital is and lowest unoccupied molecular orbital. So this is the Homo, the highest occupied molecular orbital. This is the Lumo. So we would say that psi1 is the Homo, psi2 is the Lumo. Right, and that's for ethylene. Right, when we look at butadiene, now we have to worry about 4 atomic orbitals coming together to make our molecular orbital picture. Right, so we're going to have 4 atomic orbitals. Right, that's going to be our non-bonding line. So we're going to have 2 anti-bonding molecular orbitals, 2 bonding molecular orbitals, right? And the way these things work is that we're going to have all bonding in the lowest molecular orbital, and then we're going to end up introducing nodes as we go up. So we'll have no nodes on the bottom, and we'll end up with 3 nodes on top, right? So we're going to have psi1, psi2, psi3 star, which is going to be anti-bonding, psi4 star, which is anti-bonding. Right? And usually it's easy to do the bottom and the top. Right, the bottom, we're going to have overlap everywhere. 0 nodes. The highest energy molecular orbital, there will be no overlap. So we have 3 nodes. Okay? The orbitals in between, we're going to just have 1 node and 2 nodes. So psi2, we're going to have 1 node. The orbitals are constructed symmetrically, so the node's going to be in the middle. All right, so we have overlap on the ends, but not in the middle. Right, and then for psi3, we're going to have 2 nodes. If symmetrical, the nodes are on the outside. So we have overlap just at one position, right? Final thing we have to do is fill in where the electrons are, right? And for butadiene, we have 4 pi electrons, so they're in psi 1 and psi 2. And then when we look at this and we think about what the HOMO and the LUMO are going to be, psi 2 is the HOMO, the highest occupied molecular orbital, and psi 3 is the LUMO. Okay? So with these descriptions, we should be able to understand and explain what's going on in the Diels-Alder reaction, right? Because when we do the Diels-Alder reaction, again, this simplified case, I know that we don't have a W group. We need a W group when we do the reaction for real, but when we're just looking at theoretically, we can think about it in this case, right? And so what we want to do is we want to look at HOMO-LUMO interactions for ethylene and butadiene, right? And when we think about HOMO and LUMO, right, when we're doing these reactions, HOMO behaves like the nucleophile, it's the electron-rich component. LUMO behaves like the electrophile, the electron-poor component. So when we're thinking about the Diels-Alder reaction, the diene is usually electron-rich, so that's going to be the HOMO component. The dienophile is usually electron-poor, that's going to be the LUMO component, right? And if we look at that case, what is it going to look like? So in this case, we're going to look at the HOMO of the diene, right? So that's going to be right here, psi 2, interacting with the LUMO of the dienophile. That's also psi 2, so we're going to be here. Right? And again, remember, when we're doing these cycloaddition reactions, they're always a reaction between a LUMO and a HOMO. Right? And so here's what it's going to look like for us. We're going to draw out psi 2. And if we look at our picture for psi 2, it looks like that. So this is our psi 2 HOMO for the diene. And we're going to react that with the psi 2 LUMO of the dienophile. Right? And what does that look like? It looks like that. And again, if we want to put nodes in, we can put the nodes in where they are. Right? But if we do this, we can see that we have constructive overlap at both positions. Right? So we have constructive overlap there and constructive overlap there. Right? Those two areas of constructive overlap means that this reaction happens. Right? So that is the Woodward-Hoffmann orbital symmetry analysis and explanation for why the Diels-Alder reaction happens. We have electrons in the HOMO of the diene interacting with the unoccupied orbital, the LUMO of the dienophile, and that enables us to get a reaction to occur. So this is how you're going to do the analysis for all the reactions that we're going to do from here on out. The only additional thing that you need to know is what happens when you do a reaction under photochemical conditions. Right? Under photochemical conditions, the only thing that happens, so if we're looking at what we have up here on the board, if we take ethylene, shine light on ethylene, what happens? We're going to take one electron from the HOMO and promote it to the LUMO. Right? And when we do that, the LUMO in the ground state becomes the HOMO in the excited state. Right? And this is for the excited state. Okay? And the other important thing to remember when you're doing photochemistry is that you never have two excited state molecules find each other. Reactions are always one ground state molecule plus one excited state molecule. Right? So if we were thinking about Diels-Alder reaction under light, we would think about what would happen with a ground state butadiene interacting with an excited state ethylene. Okay? And then you can see we would have HOMO psi 2 interacting with LUMO psi 3. And if you draw out what would happen in that case, you would see we would not get constructive overlap and the reaction wouldn't occur. All right, so that's an overview for the Diels-Alder reaction. Hopefully this helps as you think about what's going to happen in 2 plus 2 and 4 plus 4 reactions. And we'll talk more about this in class on Monday.